Hey, welcome to some interesting applications of calculus, building from the last presentation on derivatives of trig functions. And have you seen this before? What is he talking about here, mate? And the idea here, I'll get rid of that, is have you seen the use of calculus in up the top here, finding the maximum or minimum value of a function? I guess you have, but what we're going to do here is extend it to functions involving the trig function. For trig functions, sine, cos and tan. So come over here to this little diagram, give you an idea here of the question is, what is the maximum area of this sort of shape inscribed in that circle? Can you find the dimensions of the shape that gives you a maximum area? Or over here on this one, what is the minimum length of these two wires to firm up the poles, the pole A and the pole C, and being joined in the middle there, something like that. Or down the bottom, here's your house, and you've got to clear a 2 metre fence, which is 2 metres from the house. How long does that ladder have to be, x, y, to get over that and lean against the house? Now that's an interesting question. What's the minimum length of ladder you need there? So they are all very interesting applications, and we're going to have a look at how you can use calculus to do that. And hopefully you've had a bit of experience of calculus already and can find when a quantity has got a maximum or minimum value. Something to do with the derivative being equal to naught, I think. Is that right? Okay, we'll come down and let's have a look. And here's the screen clipping from Hayes and Harris Publications. So it might be worthwhile getting that book and having a look there as well. So here's our problem. AB is a fixed chord of a circle, and it's very important to draw a good diagram. And it's 4 centimetres long, so that's fixed. Find the measure of angle ACB in degrees, and show that x is approximately that, and then find when the triangle has the greatest area. So they're giving us a bit of a bus trip here, taking us on a journey so that we'll be able to set up to do the final step, which is finding when the triangle has a maximum or greatest area. So as with related rates that we did in a couple of presentations ago, you can see the important thing is to set up a well-labelled diagram here. And we're going to try and find angle alpha is what they wanted us to find here. And so let's label everything. Now we can call AC x, it's a variable here. And we've got angle theta. And we can draw in a little bit of a helpful diagram, a helpful triangle here. AOB, sorry. And then once we've got that, we've got equal radii there and there. So we've got two equal angles at the vertex of that isosceles triangle. So then we can work in OAM. Okay, and why are we doing that? Well, alpha here is going to be the angle that we want to find, and if we can use SOHCAHTOA in this triangle here. And what are we using? Well, the idea here is the angle at the centre is twice the angle at the circumference, subtended by the same arc. So that's 2 alpha, and then with that isosceles triangle down there, one of those is alpha, so we can use the sine. So that's a little bit tricky there to find that angle alpha, but you've got to use angle at the centre theorem. Angle at the centre is twice the angle at the circumference. So a little bit of trick there. This makes this work fairly challenging for some people because you need to have some geometry remembering the geometry. And now what we want to do is to find x, this length over here. And so in the big triangle now, that's not so bad because just scrubbing all this out and starting again here. In the big triangle, x over the sine of this angle equals AB over the sine of alpha. And we know that AB is going to be 4, okay, because it's the length there was given as 4, and then x will be multiplying by the sine of here, ABC is 180 minus alpha, take theta, which is some angles of a triangle, isn't it? So this angle is 180 minus these two. Okay, and we have found the angle alpha. So 180 take alpha will be 138.19 because we're using the alpha from up here we already found. We got guided through this solution, and therefore we've got that, and it's approximately 6 sine, and this now is in what? Radians here. We've changed the angle to radians. All right, so that's been a bit helpful because you're going to see what happens now, and then we're going to look at what we've tried to do. They've led us on this particular pathway, this particular strategy for solving the problem. So now what do we want to do? We want to find the maximum area, so let's try and find a formula. Half the product of two sides, half, there's the two sides, sine of the included angle. Okay, and that's the formula there that I've just done generically in words, the area of any triangle, half the product of two sides, sine of the included angle. So we now have our formula because we can replace x by this expression in here that we just found, and so we have the connection of the area to a single variable. And now I think you might remember what to do with that. If you want to find, and let's just revise that over here. If you have a function, let's take a simple quadratic. If you have y is something like, what could this be? It's been translated, could be x, neg because it's concave down, or a concave parabola, x take 2 squared plus 3. If you have some function like that, what is your process for finding this maximum value here? Well, first of all, we want to know the x value at which that occurs. And remember Hutty's trichotomy with a derivative. The derivative is the slope of the tangent or the instantaneous rate of change. And so the slope of the tangent here, dy by dx, the derivative, synonymous with that, is 0 because it's parallel to the x-axis. Remember that stuff. So your next job is to get the derivative of this and put it equal to 0 and solve that. So let's go and do it over here back in our problem, differentiating this with respect to theta. The interesting thing here is we've got a product, that term in theta and that one. Let's take the 12 out the front and differentiate that. Derivative of sine is neg cos. And the derivative of sine is cos, and then multiplying by neg 1, the derivative of this here, okay, and then the derivative of the other term unchanged, so it's u dash v plus uv dash for the product rule, isn't it? Derivative of sine of all of this by sine unchanged plus the sine function, the u, unchanged by the derivative of sine, over here, which is cos. So it's getting messy in these problems because they're practical. It can get quite messy. All right, let's have a look now at simplifying that. So we're going to say, let's put the this term first here, this term out the front, minus the other one, and then you can see a pattern. Sine of an angle, cos of a different angle, and then sine of the minus cos of that angle, sine of the other one. So that's the sum, products to sums sort of formula here, okay, the sum formula. And sum to a product, so here we've got sine cos minus cos sine is sine of the two angles subtracted. Okay, sums and differences there. The first angle, there it is, minus the second. So these formulae are going to be quite important, and we had a look at them in the last presentation. Okay, so just check that. The idea of the pattern sine alpha cos beta take cos alpha sine beta. Sine cos take cos sine is the sine of, what do you reckon? It's the first one minus the second one. Okay, so that's the addition formula, or here it's changing a difference to a sum of angles. So there's a whole lot of them, sums to products, there's a whole lot of formulas there. Okay, so what have we got? We've got this thing. And now it's going to be important to find when that tangent has a zero slope parallel to the x-axis, a turning point. So we want to say that is equal to naught when the angle's naught, the sine of anything to be equal to naught means that thing, that angle must be naught, or k times 2 pi. Okay, so we've got those values there. Okay, so we can then solve that and come down, and we've got these values, so naught and k times 2 pi. So I think what we're going to have to do here, that's for 2 theta. So then if we put that equal to our expression, we divide everything by 2, and we can have naught, 1, etc. So we've got here theta is approximately 1.2059. Okay, so that's the value there that we can have, because we've got only between naught and pi. You can only go from naught to pi for our angle. Okay, so what do you think about that? That's interesting. It's getting hard maths down there solving those equations. But we need to also make sure that whether this is a maximum or a minimum. So there's 2 ways for that. You can do a sine diagram, which is what we've done here. Draw a little bit of the theta axis, put on the critical value, sub in an angle to the left and to the right, and you find that the slope is positive there, it's 0 and then negative, therefore it is a local maximum, when at approximately 1.2059 or 69.1 degrees. And the idea here, of course, is you can't exceed pi or 180 because it's an angle in a triangle. So that sort of, let's just check that you've understood that back there. If you don't do a sine diagram, you could use the second derivative, because at a maximum, you've got here the idea that this would be less than naught. Okay, so here you could use the second derivative and see if it's negative at that point. Don't know whether you want to do that. It would involve differentiating this first derivative, 2.4119 take 2 theta, differentiating that to get the second derivative, and that would give you 12 cos 2.419 minus 2 theta, and then times by the derivative of this, so it'd be timesing by neg 2. Okay, and then you could substitute the value in for the angle here and get the cos of naught, which is 1. So this would come out to be negative, which checks as a maximum for that particular point. So you could use the second derivative instead of the sine diagram. This is a bit doubtful, because often the expressions for the first derivative are fairly complicated, and you will have trouble getting the derivative, again, of that derivative, the second derivative. But just remember that as a way of what we call classifying a particular turning point. Notice you cannot assume, do not assume, that the turning point you have found is going to be what they want, a maximum. You have to check it out that it is a maximum. So therefore 69.1 degrees, and that's what we want. The interesting thing here is that produces BC and AC as being equal, and therefore the triangle is isosceles. Just an interesting little note there. So there's a lot of stuff in this where you're coming back to solving trig equations when you're putting derivative equal to naught. So you've got to think about that idea as well. And so a lot of revision here. Remember, maths is often sequential and is mostly sequential and cumulative, actually. You've got to do things in sequence and accumulate the knowledge along the way. All right, let's have a look at what we've done. They guided us on this problem And so I'm going to summarise it for you. How do you go about finding the solution? Now, you've got to find a formula for the quantity to be maximised or minimised. Now, I think before all this, really, to help you do that, you're going to need to have a good diagram. As we did before with related rates, with all the information marked on it and so on. But here we said we wanted to find the maximum area, and so we needed a formula. So this time it wasn't bad. We could use that sort of thing, and we could see it from the diagram. Okay, so then this next point's important. You can't have x's and thetas both varying in there. So the book helped us because this was a sign of theta there, and these two were also varying. So we needed to eliminate those sides and get them in terms of theta. So this was very, very important. So there's only one variable left, because you know what's coming up. We want to differentiate with respect to that variable, not like related rates, where we can have a derivative with respect to time of any variables present. It still is advantageous just to have one variable in that relationship at the end. But here, you must simulate y equals a single function in x, and then you want dy by dx. You don't want other variables there. You want to differentiate it with respect to a single variable as if you're drawing its graph, and then you're going to do something with that. And that's here. You're going to then put the derivative equal to naught, and then classify using a sign diagram or second derivative, whichever is easiest, okay, to actually see what's going on there and just discuss it. You don't generally use both because that's going to take too much time to do that. Okay, so then the final step is to state the answer in the context of the question, so that you don't just end up with theta equals. Okay, you describe the maximum value of the area will be at that particular theta or whatever. They might only ask you the value of the variable to produce the maximum. You don't necessarily have to evaluate the maximum. So think about those variations. So this is a repeat of calculus done in other subjects. All we're doing it here for is to work in those functions where the variable is an angle and you're going to have sines and coses floating around. And so we're going to look at the application there. All right, come down, and here are some for you. Please try to follow the steps. Mostly the diagram will be given. Make sure all the given information is listed somewhere on your paper, because you will need all of that. That's often an escape route if you actually get stuck, to make sure you go through and have used all the information. Sometimes underlining it is useful. Putting in 10 and any other radii that are 10 here. So they haven't given you a bus trip here. Giving you a little bit, show that that's the area, and then find the maximum. So they've helped you with a formula there, but you'll have to work through how to get to that formula for the area, which is, of course, the first strategy, is to get a formula for the quantity to be maximised or minimised, and then remove all but a single variable and so on. Okay, so I'll leave you to look at that. Do the check. Very important up here. All given information. Do that check to make sure it's all on there. Okay, you could pause the presentation, have a go at those two. Work through the strategy carefully. Let's have a look at the next one. That's question 3. Okay, let's have a look at the solutions now. A few different ways of doing this first one, question 1. Okay, let's have a look at the rest of the answer. Look at the statement here. Okay, make sure you state it clearly in the context of the question. Let's have a look at question 2. You'll see the pattern there. Obtaining a formula, getting the derivative, and then classifying it. 1, 2, 3. know your work so that you know what you're trying to do. When I say know your work, know what the steps are. It's hard enough to get the answers, and you should at least know what you're trying to do. Okay, let's have a look at question 3. And the same sort of thing happening here. We want to get a formula for t. Okay, and there we have it. Interesting one here. Study this one. We're going to have to use some of the techniques from before with formulas, similar triangles, sine and cosine rule, all that sort of stuff. Then we're going to put the derivative equal to naught and so on. And then this is important here to look at stating the answer. And here we should check the end conditions or the boundary conditions, because this is a local maximum. Okay, now it doesn't mean that if the angles are at the end of the domain, that isn't also a better time. So the shortest possible time actually tends to be when theta is pi on 2 here. Okay, so the idea is to check those conditions. Just check that now. If, for example, we had a function like this, and we wanted to know when we could get a maximum, let's just do it in y's and x's, and we find the local maximum is there, and we say that's a maximum, you just got to check this end. Are you allowed to go far enough out in the value of the variable x to actually beat that maximum? That's what's called checking end conditions. So you should check the end of the domain there and the end here. So in this case, sub in x is naught and sub in whatever this x value is that's allowable. So just watch that there, checking those end conditions. Okay, let's go down and do some more. So here we are. This is an interesting problem. 2 corridors meet at right angles and are 2 metres and 3 metres wide. Theta is the angle marked. We've got that on there. And AB is a thin metal tube. Can you get it around the corner? Must be kept horizontally. Okay, so you can't bend it. You're not allowed to stick it up towards the ceiling. Show the length of AB. So they're helping you here. Find a formula for that length. Show that the derivative equals naught then, and determine the length L, and can comment on the significance. So they're taking you through the strategy, and if you are unable to do that length, you can still use that length and go on to complete the problem. Okay, don't stop because you can't do the one part. This is what I'm referring to as a bus trip. They're hinting at what the next stop is, what the steps are, for example. Okay, so let's have a look at the L and what L is, this length here, A plus B. So I think you can see you can get L most easily if you get A. So cos theta is 3 on A, sin theta is 2 on B by the basic Sokotoa rules. And so A is multiply both sides by A and then divide by cos theta, same thing here with B and sin theta. So you've got those two expressions. Now the length is the sum of those. So I guess when you looked at that, you could see that it could be split into this triangle and add up those two hypotenuses. Okay, so we've done the first thing. So it's not a bad idea to put here as required. Okay, and now let's go on and find the derivative. And so if we look at those two parts of two functions there, to make a part of L, it's this one, and sine theta to the neg 1 as well. So let's differentiate this one, differentiating with respect to cos theta, so that's doing the power function first, it's to the neg 2, and then we have to multiply by the derivative of this in there, this is neg sine theta, then we do the next term, it's 2, it's just a constant out the front, doing this, it's neg 2 sine to the 1 less power, so that's differentiating the power function here with respect to the variable sine theta, calling that the variable there, and then multiplying by derivative of sine. So this is the chain rule, isn't it? The function of a function or chain rule, and the time you invoke it is when you have, let's just tidy this up here a bit, when you have obviously a function done on another function, or the function of a function rule. You have to do this function and get this first derivative, and then this function. So overall you have a chain of two derivatives, if you like. Okay, so now let's put it together. A negative by a negative is a positive 3 sine theta. Neg 2 power is cos theta squared in the bottom line. And then take, and this is 2 cos theta in the top line, and this negative exponent means sine squared in the bottom line. So we can get that all together over a common denominator. This has been times by sine squared, so you must multiply the top line by sine squared. This has been multiplied down here by cos squared, multiply the top line by cos squared. So we have that result, and let's now have a look, and we want to put that equal to naught. So we'll take, when is a quotient 0? Remember, implies the numerator is 0, not the denominator. The denominator being 0 would make the thing undefined, so we're only going to focus on the numerator, and that's going to be 0 when the two pieces are equal. So solving that, let's get a package of tan. So divide both sides by cos cubed, and then by 2. So tan cubed is 2/3. So tan theta is the cube root of 2/3, which is approximately that. And that's what they asked us to show. So now we want to look at whether this is a maximum or a minimum. So draw a sine diagram. And here's our 41.4 degrees, and we could sub in a value to the left and to the right. And if we subbed in 30 degrees, then dl by dt is negative, and if we subbed in 60, it's positive. You really should indicate the values that you've used here to show that you have checked the maximum or min, or the sign of the derivative. This is negative, so it's going to be sloping down, then there's going to be a turning point, and then going up. So that satisfies the idea that this is a minimum. So therefore it's minimised when theta is that, and you can sub it back into the expression for L back in part A, and then we've got that length. But notice we're ignoring the width of the rod, okay? But if we ignore that, then we've got that. If it's a big, wide, thick rod, then you'd have to take that into account, and you wouldn't be able to have such great length going around there. Right, so just that's a comment about your answer, that we're ignoring the width of that rod. Okay, well, let's have a look now at doing some of a nature of the same sort of nature. So here's a couple I mentioned on the first screen now. So here's a variation. You'll need a diagram for this, okay? And so that's a very important first step, which I left out in the strategy. Usually that will be given to you, and this is the usual way, a bit of a bus trip, a few hints. But you as a budding young mathematician should be able to do it without those. So pause the presentation, have a look at those first two, 4 and 5. Let's have a look now at 6. I think there's only the 3, so we'll see if we can get them all on. Now we can get 6 and 7 on, and it's another one I mentioned before. Make sure you put all the given information on there. This is similar. Okay, so pause it and have a go at least one of those. I'll show you the solutions in a minute. And then question 8. Okay, so here this is a pump house, and you're pumping water to 2 homesteads, and you want the shortest length of pipe. So the length of pipe is here and here, the total length of that. So again, they have bus tripped this, given you some ideas. Do this, then show this, etc. I think this is a very important question to go through, because it involves some very interesting derivatives here of what you need to do right the way through, some implicit differentiation. Okay, let's have a look at the solutions then. So here's question 4. Again, very similar to the example we just did. And question 5. We'll have to have a look at the last little bit of 5. A little bit of similar triangles work here. I think you can identify that from that diagram. Let's have a look at B and C. Okay. Then at 6. Okay, the first bit of there, and then we'll look at the derivative. Okay, putting it equal to 0. Getting messy. Sometimes, because these are practical problems, they can be quite messy. And let's look at 7. Okay, bit of geometry happening here. And we'll just go down and look at the differentiation. Okay, so lots of work here with the derivatives. Bit of a challenging one there. Okay, and the last one, important question, this one, bit of maths in this one. That's A and B. And then let's have a look at C. And we'll see if we can get it all on. No, C and D. And then finally, the last little bit. This is an interesting question, this one. We really need to concentrate and work on the solution to that one. All right, so I hope that reviewed a bit of the stuff you've done before on finding the maximum and minimum values. It's not in this course, only the maximum and minimum of sine and cos is actually in this course, but you can review some of the stuff on calculus elsewhere. And I hope you're having fun now that you can get the derivative of trig functions. It opens up a whole new world of possible questions you can answer. Okay, well, we're going to go on with related rates in trig land in the next presentation. So I'll catch you then. Cheers for now.